Hi, everyone. This is a video about a homework problem that I wrote that, in retrospect, is a little bit less clear than I would have liked. So the purpose of this video is to help you understand the intent and the language in this problem so that you're able to understand it and apply it to future work. Here's what it says. It says that the cross sections of two beams are depicted in the table below. One is a T shape and the other is an asymmetric I shape. And we want to imagine that both beams have been bent about the centroidal z-axis. And that centroidal z-axis is this one right here. Let me use an orange color for this. Okay, so there it is right there. Here it is right there. Problem goes on to say that each beam has been subjected to positive internal bending moment about z. The cross-sectional area above the neutral axis will experience compression, and the area below will experience tension. Okay, so we have two asymmetric cross-sections, but compression on top, tension on the bottom. Then there's a reminder of what lowercase c means. C is a distance. It's the maximum of y bar and h minus y bar, and it gets you to the worst case stress. So that part I think is relatively straightforward. So let's fill out the first table, the first row of the table first. So it says, what is C for this beam? So what I want to do is start here at the centroidal axis, and I want to go as far away as I can, which is 6.5 inches to the extreme fiber, the bottom fiber. So we have a distance of 6.5 inches, and we want that to be, it's just a magnitude, right? So if you just write 6.5, that's okay. I feel like the absolute value signs maybe emphasize that, but we just want to go the maximum distance, be it positive or negative, to get to the extreme fiber. Over as we go to the asymmetric I-shaped member, the farthest distance we can go is up here to the top fiber. So how far is that? It's a distance of 120 millimeters. And that distance, again, we could do a absolute value sign there if we wanted to do so. Make sure that's clear and not like another one. Okay, so we could do an absolute value sign there if we wanted to do so. And so either with or without the absolute value sign, that is the best answer to this first row. And again, I fully acknowledge that this problem needs to be kind of reworded and workshopped a little bit. So I apologize for that. Before we get into the tension and compression, I'm gonna turn down that. I'm gonna move this layer here. Give me 1 second to get my layers where I want them to be. Okay, we're gonna turn this one down. And here's what I drew in advance. So what I wanted to show is what these cross sections were actually experiencing. So the problem statement says that they're in positive bending, but there was no free body and there was no loading shown or anything like that that would allow you to deduce that if you didn't just read the problem carefully. So here what I'm doing is showing each beam as a simply supported beam, so vertical reactions near and far, and then the pink arrows, the pink vectors pointing down, are the loads. And so we're going to see positive bending in both of these arrangements, compression on top and tension on the bottom. All right, let's go back to our main table here. And for the rest of these, I think it's just some of the language that I tried to be really clear, but did not succeed in my goal. Here's what it says. If asked to solve the maximum magnitude of flexural stress, okay, so if I want to maximize this, and magnitude means I'm considering both tension and compression, what distance would you plug in to the flexural stress equation? Okay, so we want a magnitude of stress, but the distance term here is going to be either positive or negative because our origin is right here at the centroid. So let's think through this. For the T-shaped section, I know that my maximum magnitude of flexural stress occurs 6.5 inches away. It's this bottom fiber here. How do I measure from the origin down to the bottom fiber? I'm going in the negative y direction. So the answer to this would be negative 6.5 inches. And to be a little more specific, I would plug in negative 6.5 inches here. I would have this negative and this negative make a positive. My worst case stress is tensile. Remember that little sketch we did? Where did it go? Not that one. Yeah, this one. Okay, so tension on the bottom. So it is tensile. And the signs will all work out as long as you include the negative sign with the 6.5. So I think the confusion is magnitude was for this term. This still has a sign. All right, let's do the same thing for the T-shape. Okay, so we know that our worst case flexural stress lives at 120 millimeters away from the axis of bending. So I start at my centroid, I go up to the top fiber. That's in the positive y direction. That's why this answer is going to be plus 120 millimeters. Okay, and of course you don't have to write the plus, it's assumed to be there if it's not written. But in order to be extra clear in this solution, I'll go ahead and leave the plus in my solution. Okay, let's read the next prompt. It says, if you're asked to solve for worst case tension, what distance would you plug in to the flexural stress equation? All right, distance for maximum tension. Okay, so this is asking about the bottom fiber of both of these cross sections. So I want to start at the centroid, measure down to the bottom fiber. So these are both going to have a negative sign. Okay, so how far do I go? 6.5 inches in the negative y direction, 80 millimeters in the negative y direction. The last question's asking about compressive stress, and I'll switch back to an orange color for this one. So if somebody asked you where is the worst case compression stress, compressive stress, what distance would you plug into the flexural stress equation? Well, I want compression, so it's going to be this top extreme fiber since my beam has positive bending, compression on top, tension on bottom. And so how am I going to measure from the centroid to the top fiber? I want to plug it positive 3.5 inches into the equation and positive 120 millimeters into the equation. Let's spot check this last one and make sure that our answer makes sense. Okay, so I'm going to pretend like I'm plugging into the equation. To do that, bear with me here for a second. Just turn down everything I see there, and I'm going to switch to a black marker here. All right, so my equation is sigma equals minus my over I. We want a maximum compressive flexural stress, so we're expecting that that sigma is going to turn out to be negative. Okay, let's check it and see if it does so. So for my y coordinate, I'm going to be plugging in a positive sign there. My moment is positive per the problem. So the negative sign, so negative times positive, that gives me a net negative sign for compression stress with sigma. So that is the intent of the problem. It was supposed to be an easy, quick checkpoint on what to plug into the equation in order to get different outputs. And apologize that it was not super clear as written, and it is on my to-do list for one to workshop and think of a better way to emphasize and assess this particular concept. Thank you for tuning in and have a great day.